Muy bien, pues muchas gracias por venir aquí hoy, luchando contra los elementos y la tormenta que ha habido en Madrid, las que todavía quedan por venir. Luis Dogá pasa unos días en Madrid, en camino hacia la conferencia de Papis y yo en Boston, y bueno, pues tenemos mucha suerte de que se preste a darnos esta charla. Va a ser muy breve, por tiempos tendremos 35-40 minutos. Y os animo a que le hagáis este tipo de preguntas, es una ocasión muy buena de tenerle aquí. A ver si entre todos podemos convencerle para que venga de ponente a Meetup Spain, que tendrá lugar el 26 y 28 de noviembre. De acuerdo, pues eso es todo.
Gracias, Rubén. Hi, everyone. I'm sorry I'm doing this in English, but my Spanish is not good enough. I can order food and that sort of things, but for doing that sort of talk, it's going to be tough. Okay, so we're going to talk about real-world predictive apps. Before we get into the technical stuff, and there will be a demo at the end of the presentation, but before that I want to introduce what sort of predictive apps can be built using data and machine learning. Yeah, recording. And the presentation is being recorded if you want to watch it again. I'll share the slides, but yeah, this is being recorded. So, you've probably noticed that we hear people talk about artificial intelligence more and more. It's kind of everywhere. It's who's heard of this AlphaGo? No? Doesn't sound familiar? No, you know, one person at least. It's a game that's mainly played in Asia. I mean, at least originally. You could sort of compare it to chess in the sense that it's a board game. There's two opponents, and artificial intelligence has been trying to beat humans at this game. So in '97, I think the AI developed by IBM called Deep Blue beat the world champion, Kasparov. And what's funny is that you know, for a long time people thought that Go was super difficult because actually the number of possibilities that you have on this board is much bigger than what you'd have in chess. And for a long time people were thinking that, you know, Go is impossible, okay, machines can beat humans at chess, but Go is going to be super difficult. And what happened is that a couple of months ago, Google developed this algorithm called AlphaGo. I can't point at the TV yet. Called AlphaGo that beat the world champion at Go. So there was a lot of buzz around that, a lot of talk about AI and, you know, how it could replace humans, and this result was extrapolated to, you know, all sorts of different areas, and the consequences were that people imagine are sometimes a little bit crazy. But anyways, it's interesting to see that, you know, people are talking about AI again, and it's not just, you know, those sorts of games. It's a sort of very narrow area playing games. It's actually useful in the real life. So this is a screenshot of Amazon, and here everything that's being blurred out is content which is not customized for the viewer. So there's a lot of real estate which is powered by predictions of what people would be interested in. Okay, that's e-commerce that's been around for some time. But what's relatively recent is AI in our smartphones. So this is iOS. If you search for things on iOS, it also shows suggestions. So these Siri suggestions, there are contacts in there, so people you might want to text or call based on the current location and time and date, and also suggestions of applications that you might want to use, again based on the current context. So your phone predicts what you would be interested in doing and what your next move is going to be. This is an application that's not developed by Apple this time, but it's just on the App Store. It's called Hopper, H-O-P-P-E-R. And what it does is that it predicts how prices of flights are going to change through time. So in this case, I was looking for a Paris-Buenos Aires flight, and basically it tells me what the optimal time is for booking that flight. I'm not going to go to Buenos Aires in the end, but it's funny to see these predictions of the evolution of the price and to sort of see what will be the right time to book the flight and to predict what the price would be. There's something also that's quite innovative, I think, which is an application for the public bikes in Bordeaux. So I'm from Bordeaux in France, and we're more known for the wine we produce than the applications that we develop, but there's some pretty nice innovation in Bordeaux as well. And this is, I think, that there was a world first where people came up with this application that predicts availability of bikes in the future. So imagine you want to rent a bike from the public bike stations, or you want to leave your bike somewhere. This allows you to see whether or not you'll be able to find a bike or to find a slot to park your bike. So it predicts up to 12 hours in advance availability of bikes at bike stations. Okay. In emails also, you see quite a lot of machine learning in emails. I think the first use case was spam detection, using data of examples of emails and whether or not they were spam. People were able to build predictive models, and now there's all sorts of other areas. So this is a pretty different classification problem where you would analyze the content of the email in order to predict whether the sender is requesting me to do something. So is there an action to be performed by me? And if so, it creates a reminder it creates a task. So in that case, that person was asking me to send him a URL. The system, which is Google Inbox, detected that someone was asking me to do something, and then it created this task, this reminder automatically. There's even people who think that up to 50% of the applications that we have on our phones have some predictive components. So it's fair to say that AI is everywhere, and it's going to get bigger and bigger. Some people predict that it's going to be the next big thing. That's actually a relatively old quote. I think it's a couple of years old. And this one, okay, so this is Big Data Spain. What should we do with all this data? It's all this data is good for adding intelligence to us humans, but how do we add intelligence to the machines so that they can do things automatically? So we need some sort of predictive components. I want to give another example because, as Ruben was mentioning, I'm behind the PAPI's conferences. I like this use case because it's kind of outside of applications. Outside of desktop and mobile applications. That's more real life. It's the Starup Battle that we've had at the previous conference and that we'll have at the next ones, the Boston one and others. So the concept is pretty simple. It's a startup competition where startups pitch, and then so usually what happens is that there's a jury that selects the best startup and then they win some money. The difference here is that the jury was an artificial intelligence, so no human involved in choosing who gets the big check. This AI materializes itself in this little box, and you can see that there's a microphone pointing at it, so it speaks. And what's funny is that when you would use, for instance, something like Siri, you would be the person asking the questions, where here it's the other way around. This device asks questions to the startups. They answer those questions. The answers are processed by the system, and then I couldn't get a better picture of that, but you can see that there's different scores. So there's 4 startups, and then this is the winner. All of them have scores between 0 and 100. Yeah, if you want to recap, startups pitch, the AI asks questions, they answer the questions, you get a score, and the startups with the highest score wins money. So what's interesting here, I think, in comparison with the other applications, is that there's a lot of money being involved here. So people are trusting AI, and in this case, AI being powered by data and machine learning to make decisions with a lot of money. Okay, so it's been developed by these guys at Open Future and Big MN. I won't speak too much about them. Actually, I'm not planning to speak about them, but this gives you an idea of what sort of data they consider. So data on the idea, the business plan, okay, but also the team, the competitors, so all these sort of things. You need data to understand what's going on, and then you can learn from that data. They've actually built this, so it's not, this intelligence is not only being used in these startup competitions, but they're going to be used by venture capital funds to better choose which companies to invest in. Okay, that was kind of a long introduction, so let's have a look now at how it works. So you need two things in order to create a predictive application. If you've got only one of these things, you might do something, but it's not going to be a predictive app. You need data, and you need machine learning. That's probably my oldest slide in the whole deck. That's a spam, right? Hopefully. I was in fact in 2013, so that was spam. Okay, what type of email is this? Is it spam or is it not spam? Well, those sorts of questions, when you ask questions like that about objects, we speak of classification questions, classification problems, or the which types of questions. And this is what you'd call the input. The answer to that question is what you'd call the output. The way machine learning works is that you get a bunch of inputs and outputs as examples, and you can train a model by somehow analyzing that. What's interesting with this model object is that you can use it with new inputs that you've never seen before, so new emails that you've never seen before, in order to make a prediction on what the output should be. So is it spam or not? And we're all very familiar with that concept, but it's pretty magical to have a machine automatically decide, without any human looking at the email, it just decides whether to put it in the spam box or to keep it in the inbox. What this also means is that if we don't have the examples of inputs and outputs, it's not going to work. So at some point, someone had to devise these examples, had to label emails into spam or non-spam, which can be a tedious task. How do we get that model? We'll speak about that later, but let's just assume for now that the model exists. There's a way to create that model from data. Another example I quite like is real estate. Everyone knows a little bit about real estate. And the type of question that you'd be interested in is predicting price. So when you try to predict a number, usually you speak of a regression problem. This would be, actual data. So, sorry, this is small data, but you get the idea. Each row corresponds to a real estate property, and each column corresponds to one way to characterize that property. I've highlighted in yellow all the real estate properties for which we know all the information. And what I'm assuming here is that, okay, I want to predict the price. So the price is going to be my output. When I don't know the price, well, I've got a prediction to make, so I've got to fill in those missing values. When the rest of the other values, so number of bedrooms and so on, that allows me to represent my new inputs. So new inputs are in blue, and predictions to make are in orange. So essentially, machine learning is about filling in missing values. Pretty simple, right? You have to focus on one column, and you do have to have examples also. So if you don't have enough examples, enough guys in yellow, then it's not going to work. But and you have to decide. I'm going to just focus on that price column. There might be other missing values, but I'm not going to be able to do anything about those. By convention, the last column usually represents the output, so that's something that's useful to keep in mind. Okay, where do I want to? Okay, everything. Yeah, the model building. It all relies on the data you've got. So everything is based on these examples. So you better get them right, and you better get a lot of them if you want to be able to learn something that works. One way to see machine learning is a set of techniques that are somewhat intelligent, because they're doing things that we weren't able to do automatically before. And the intelligence relies entirely on these examples. It's kind of similar to what we do. I mean, at least in real estate, we would, if you would move from Madrid to Bordeaux, and you wouldn't know what the real estate market is over there, you'd have a look at the properties for sale to sort of try to understand how the characteristics relate to the actual price, and then you build with all these examples that you would see, you would build a model in your mind, and that model would allow you to make predictions. If you see a new house, you see the characteristics, you'd be able to say, okay, that's too expensive for me, or I can probably afford that. So you've got your pricing model in your mind. There's all sorts of possibilities beyond these very simple examples. Everyday use cases, I've mentioned a few. Real estate, stamp filtering. So for each one, I'm giving the input in blue and the output in orange. I'm not really saying how these inputs are represented. I'm just saying that the input object is a property, but then you have to think about, okay, how do I characterize these inputs? So properties with numbers, with data, and how would I collect that data? Spam filtering, you get an email, you want to predict, yes or no, this is spam or not. City bikes, so for predicting availability of bikes, you would want to find the relationship between the location and the context. So in context, it's very, you could put anything in context. You could put the weather, and it's up to you to sort of try to model the context and see what might have an impact on the number of bikes. Startup competition, where you get a startup, see how you represent it with the team and that sort of things, team product, and you want to predict whether it's going to be successful in 1 year, 2 years, and if you predict yes, then you might want to invest. Some other examples that might be useful in your company, you've got customers, you might already plot the churn rate. So churn is when people are customers and then they stop being customers. So maybe they have a subscription to your service and then they cancel that subscription. So you lose them as a customer. So that's churn, and that's what you want to avoid. So you want to predict in advance people who would churn so that you could do something before they actually churn. You could convince them to stay. Optimizing pricing, where if you change the price, sometimes you can change the number of sales, and ideally you'd want to predict the number of sales for a given price point and see by multiplying sales and price which price would maximize revenue. Anticipating demand. There are certain industries where this is super useful. For instance, the food industry. Imagine you're selling perishable goods like meat, for instance. Meat goes bad pretty quickly. You would need to predict the number of sales in order to ship the right amount of goods. So if you ship too much, then what doesn't get sold goes bad and just goes to waste. If you don't ship enough, then you could have made more money. So you need to find the right amount of goods, of products to ship, and for that you could predict what the future would be. So given a product being sold at a certain store, at a certain date, how many am I going to sell? And I've tried to give some examples of companies that actually implement these sort of things. The whole point of using machine learning is to let computers go through big amounts of data, and yeah, you could say that big data could be just 20 examples with 20 columns. It is big because the other alternative is to have a human go through all these examples and try to understand how everything works, and it's just too big for us. So yeah, for a human, 20 by 20 would be big data. But anyways, the idea is to have the machine go through all your data to create automatically the right rules that allow you to make these predictions. So obviously you could make manual rules. You could say spam filtering. If the spam contains Viagra in the body, then it would probably be spam. If the email contains machine learning in the body, then it would probably be not spam. And the good thing also with having these rules learned automatically is that if things change in the world, so you record new data and you can adapt. So you can just retrain the models and they adapt based on the new data. You don't have to have someone actually rewrite the rules. Just push a button and everything adjusts. Okay, some business use cases. I'll try to list them in 3 areas. First one is getting more customers. It's still useful, yeah. Getting more customers, so you can either get more customers or just make sure that those that you have don't go away. Reducing churn, I've talked about that. The other interesting thing, I should have written lead instead of customer, but imagine that you've got a lead and you want to see if they could become a customer, but if it costs money or time to convince them to be a customer, maybe you want to prioritize these leads based on the sort of revenue that you can expect from them, and then target the big revenue ones first. Serving customers better. Okay, 2 examples, and the last one is using predictive enterprise apps. I'm going to say something about that next, but let's have a look at these 2 examples. Providing the right products. That's kind of like recommendation, where you have a customer and then you want to see if they would be interested in a given product. If they would, then you would promote that product to that customer, and then you'd make a sale. Optimized pricing, I've talked about that just before. And the last one, serving customers more efficiently, so predicting demand. And the other example I had was just automating tasks. So for instance, in the finance industry, part of what people do in that industry is give money, lend money to other people. A big part of, I guess, their jobs. So imagine that someone is applying for a credit to do something, to buy a house or to fund the company or whatever. You want to predict whether or not they will repay that credit in time, and then based on that prediction, you would make a decision. Okay, I'll give the money, or otherwise maybe I'm not sure. I'm going to ask someone else's opinion, or maybe you're pretty sure that they won't repay on time, so you just automatically reject. So that's just one example, but that's the sort of things, classifying things like that that we sometimes do as humans, and that can be replaced by machines. Okay, 2 examples of predictive enterprise apps. One of them is social media filtering. So imagine that you've got a very big brand and it's on Twitter and a lot of people are mentioning your brand. Sometimes they tweet about it, but the tweets are not very useful because it's just maybe they're just joking. Sometimes they just I forgot what type of not useful things they are, but there are many types of non-useful tweets, and others that are useful because you would want to take action. For instance, replying or retweeting, or what else? Yeah, basically that's it. You'd want to reply or retweet. So if you've got a lot of tweets that mention your brand, how are you going to filter out the noise to just focus on what you should actually do about these tweets? Well, you could just predict which ones are actionable and which are not, which is something that Amazon does. They've got their own system for that. And yeah, so the social media team just has to focus on the tweets that are predicted to be actionable. There's, as you could guess, for a brand like Amazon, I think the particular example I had in mind was Amazon Web Services. There's a lot of tweets to process. So if you can filter out all those tweets that are not actionable, then you make the lives of the social media teams much easier. And as you can guess, there's going to be a lot of predictions to make, because you have to make one prediction per tweet. And if people tweet a lot about your brand because it's very popular, it's going to be pretty tough on the machine learning side. Message routing, so that's a use case where you want to, so a customer sends a request asking you to do something, or maybe to just ask you a question about a product, and the request is not that simple, so there's only a couple of people in the customer support team that know how to reply to that request, how to process that request, and maybe you want to predict who these people are, so that you can just route the message to them, and you have faster response rates, instead of just saying, oh, I don't know, let me see with a colleague, and then you send to the colleague, and then they say, oh yeah, no, not me, forward that to someone else, and you waste a lot of time. And people predict that using these types of predictive apps, that's going to improve everyone's productivity. So it's worth thinking about. There might be a use case in your company where you could simplify, you could make the life of your colleagues easier. Okay, I just wanted to take a little bit of perspective on all this technical stuff and try to see where this fits in the big picture. So, real world machine learning, you don't just want to make predictions. You want these predictions to be used somewhere to create some value. Let me check how I'm doing on time. 7:45. Ooh, I'm gonna have to speed up. So there's imagine that you wanna, you're doing churn prediction and you wanna send promotional offers by email to all these customers that might churn because you want to make them stay. So you'd have to do a bunch of things. First one is to compute what are called feature values for a given input. So an input is a customer, and a feature value is one way to represent the customer. Features in the real estate examples were number of bedrooms, number of bathrooms. So how do I represent my inputs? In order to create those representations, you might have to hit different data sources, aggregate them, merge them, that sort of things. Then you need to create your base of examples from which you can learn your machine learning model. So you need to collect that training data, both inputs and examples of outputs. You need to create a predictive model, okay? You need to make predictions, sure. But then you also need to provide the optimal decision based on your predictions. So sometimes it's relatively easy. Other times, in particular for the example where, well, even this example, for predicting churn and preventing churn, you'd want to take into account the uncertainty in your predictions and the revenue that each customer brings, and also some constraints that you don't want to send them too many emails, otherwise they would get fed up. And you want to take into account the promotional offer, what cost does it have for you, what is the success rate of those promotional offers. You want to take all this information into account in order to provide the optimal decision. Who should I send these offers to? And then once you've made that decision, you actually have to apply it. So you actually have to send the emails. All these software components, right? So starting from the bottom, you've got the application-specific one, you've got the sort of optimization one, providing the optimal decision based on the predictions. Machine learning is here. right? And everything that's before, so computing the feature values that represent our inputs and collecting the training data, that's data engineering. So you probably have people who can do that at your company already. Okay, I'm gonna just skip through that. Otherwise, oh yeah, that's a book I wrote, but I don't have time for self-promotion, unfortunately. And I'm sorry, the computer's being a little bit slow. I'm going to go straight to... Wait, no, actually, that's interesting. So, yeah, I've been thinking for some time about, what's the best way to teach machine learning to people who are new to it, and in particular developers. And a lot of people, they like to teach the actual machine learning techniques, the algorithms, how they work, and so on. Turns out you'd be able to have a better look in the slides when I share them, but turns out that most of the time there's one type of technique that works really well, called random forest. So, in practice you can just use that and not worry too much about what sort of technique you're using. I'm not sure you can see that from the back, but this is the workflow of doing machine learning in the real world, and the bit where you actually apply the machine learning algorithm is here, train model, develop model and train model. There's a bunch of things to do before that, so collecting data and preparing it so that it's in the right format to be fed to the machine learning algorithms, and then you would need, after you've created those algorithms, you would want to make sure that they do something useful before you publish them, and once they're published and they are being used in the real world, you would still want to monitor what they do to make sure that they're not breaking anything. And it turns out that this is what takes the most time. So maybe it's not worth spending too much time on the actual learning techniques, on the actual algorithms that allow you to create those models. This is another way to see things like the things that you need to do before you build your predictive model. So define the right problem, think about the best features to represent your inputs, think about when you will need to make predictions and how often. Okay, prepare the data set, that's obvious, but also once you've got a data set, you need to figure out when you need to create those models and when you would need to update them with new data. That's the sort of things that you have to think about, I think, before actually implementing anything. And after you've built your predictive model, well, okay, you want to make it run somewhere, so it might be better to run it on some dedicated server or container. But how do you package and deploy something that a data scientist might have created on their laptop? How do you make that production ready? How do you transfer that from the laptop to the production environment? And there's a language disconnect, so most of the time these are the sort of languages that you build your apps in. Maybe PHP also is a pretty popular one for web applications, but mobile apps or desktop apps, you've got Swift, C++, that sort of things. And the popular data science and machine learning languages are none of that. They're R and Python. I think that there's a bias to R in this group. I mean, so I've heard. I don't know. I'm a Python guy. So sorry for all the R guys. Anyways, it doesn't matter what you do, whether R and Python, because what you're going to do is you're going to create an API, a REST API, and put it more simply for those who don't know the REST acronym, an HTTP API. So how do you package and deploy production-ready models? Yeah, that's the problem I was just mentioning. The Microsoft people call that the last mile problem, because it looks like you've done everything, and then there's this last mile to go, like you're running a marathon, and then the last mile is actually seems longer than 1 mile. Oh, I've said that already. Sorry about the repetition. And yeah, you need all these components that we've mentioned, you need them to work together, to speak to each other. So why would we want to care about application programming interfaces, APIs? Because that allows different software components to speak to each other. Provide interfaces for those components to access each other's functionalities, and one nice thing also is that you can separate concerns. So you can sort of hide the complexity of certain bits of the whole application. So there's two things, as we saw, there's two things in... I'm not pointing at the right thing. Maybe it's low on battery. Just, sorry about that. Yeah, much better. Two phases, training and predicting. Training model and predicting with model. So you're going to have two core methods: creating model, typically with a CSV file, and then making a prediction, again using the model and the new inputs. And as I've said before, by convention, the outputs are going to be in the last column of your data file. Why REST APIs and not just Python or R API? Because the nice thing about it is that you could have communications but across different machines via the HTTP protocol, and you're using the same architectural style as the web. So yeah, you could make your components speak to each other via HTTP, and the nice thing about that is that it's developer friendly. Whatever the language you're using, platform you're using, you're going to be able to make HTTP calls. So yeah, that solves the language disconnect issue. What is a REST API? Okay, very quickly. You've got a resource that you've got resources, so everything is a resource and you can access it via its URI, and you want to perform operations on resources, like creating things or deleting things. And here, for instance, imagine that we've got users and one of them is called Tom, and I want to delete Tom. So curl is that's a command to issue HTTP requests, and when you're sending a request, you can also associate a verb to that request. You can associate a type of request. So I'm sending a delete request to that URI, which probably means that I want to delete this resource. So that's a very simple example. And we're going to do similar things, except that we're not going to use delete, but we're going to use post in order to create predictions. So the resource that we will access will be a model, a predicted model, and we're going to hit that model, send a request, a post request with the input for which we want a prediction, and yeah, it's demo time. Alright, I'm going to try to make that quick because I think the pizzas are waiting. Oh, actually no, I had a couple more slides here, sorry about that. We're going to do this bit, creating the predicted model from data manually, but what we will try to automate is the second one. We're going to create an API for that. You could also create an API for the previous components, for all these components, but I'm just going to demonstrate that, the API for providing prediction. And I'm going to use Azure ML, which you can also use for free, so that's nice. There's a guest workspace. You don't even need to have an account. What I use is the free workspace. Let me just click on that. And let's see. So that's what the should be loading here. That's what the workspace looks like. So there's what we're going to have a look at is notebooks, because notebooks allow us to program in Python. You can even do R on Azure, but I'm going to make a demo with Python. And we'll use this notebook, which is a Python notebook tutorial on Azure Machine Learning Notebook. We'll be using the Boston housing dataset, which is a pretty standard dataset for doing experimental machine learning. And yeah, that's where we are defining the actual data we use, defining X and Y. X are the inputs. Remember the data cloud that I had before? X are the inputs and Y are the outputs. And okay, cool. So I can just show the rest live. We go to notebooks and create a new one. Okay, here it is, tutorial on Azure. Taking a little bit of time. Let me see if I've got other things to show. Yeah, I'll have to show that later. So that's a notebook. Who's familiar with notebooks in general? Yeah, not that many. Notebooks are essentially web pages, except that, so they're running on a web server, and on that server also runs here a Python kernel. So the job of the Python kernel is to execute bits of Python code. So this is a bit of Python code, that's a block of Python code. I can actually edit it. I can write whatever I want, whatever code I want. Like for instance, and of course it's not working because I didn't put the quotes. And hey. So I can just run that by pressing Shift Enter. And yeah, what happens is that the server that's serving this web page is linked to that Python kernel. So when I press Shift Enter, it knows that it has to send a bit of code to the Python kernel, gets the output back, and displays it here. So that's the code I was just showing, and let me just zoom in so that you can see it from the back. Using a machine learning library that's called scikit-learn, that has a bunch of algorithms included, but also datasets, sample datasets, including that famous Boston dataset. And let's see what that does. So it is printing the shape of X, so that's 506 inputs, and then what's that? 13. That's the number of features, and that's the labels of the features. So there's a link if we want to learn more about what this dataset is. We can look it up, and essentially it's about neighborhoods of Boston, characterizing neighborhoods, and the last attribute that we want to predict is the median value of houses in thousands of dollars. So you see that the predictions are not very big, but you have to think that it's thousands of dollars, and I think that the data set was gathered not in 93, but I think it's even older than that. See, creator, 78 apparently. It's a very old data set, so that explains why the values are relatively small. So here what happens is that we're creating a linear regression model, which is one type of model that's pretty simple, and as I said, you might want to try something different. LM, that's going to be our model. Fit is the equivalent of train, so that's when we train the model from the examples X and Y. And yeah, in the slides I've given some code that you could use instead of the linear model. You could use these random forests. I'll leave that as an exercise, and you can compare the performance value you get with random forest and see that it works much better. And then there's a number of things like, trying to see what the model looks like, but let's not bother with that. So here I think this is just to evaluate the model. We don't really need that. Yeah, these bits are just for evaluating the performance of the model. What's interesting is these numbers between 0 and 1, or up to 1. The closer to 1, the better it is, and you can compare that to what you would get to... No, sorry, that's not what... Oh, okay, that's root mean squared error and relative absolute error. Okay, so yeah, no, sorry. The bigger the error, the worse the model is, so you can just try with the other bit of code later with random forest and see that you get a smaller error. What's interesting is this bit. So what happens here is that I need to predefine a bunch of variables. What's the workspace that is being used in Azure? Okay, that's boilerplate code. Here's the interesting stuff. We're going to set up a web service. We're going to create our HTTP API. We define here, so that's the bit of code you'd have to customize if you would be tackling a different machine learning problem with a different data set. You define all the features, so which type of numbers represent your inputs, and what sort of output you send back. So here it's going to be a number which is float, which is going to be the predicted median value of real estate properties in the given neighborhood. And you define a function called demo service. Okay, takes in all these values that allow you to characterize your input, so your neighborhood. Sorry. Creates that vector features and send that vector features to the model to get a prediction. Okay, that's what this method does. Demo service. So we can have a look at. So there's no API yet. Right? You can see that it works. Give a bunch of values, it gives us a prediction. So like I said, it's in thousands of dollars. And here we wanna know what the we wanna know the URL and the API key, so we can authenticate it. I think it's done here. All right, it just doesn't output the values, but what it says usually, and especially if you're using the free service, it's a little bit slower than the professional version. But it recommends that you wait a few seconds, and yeah, last bit of code. I'm wrapping up. Last bit of code is a request made in HTTP to the API. So I'll just go over that big block of code, defining some data. So actually 2 inputs. There's one array here of values and a second one here. So asking for 2 predictions. And you can see that we are using the service URL that we got from when we deployed the model. So that was super quick, as you saw. It's pretty straightforward with Azure, and defining the headers of the request, so that's HTTP stuff, right? And sending the body with those headers to the URL of the web API. So that's something that here is being done from Python. We are sending an HTTP request from Python, but you could do it from anywhere else. And it's executing. It might take a couple of seconds because it's the first time we're hitting that web service, but it should be sending back a reply in JSON. So that JSON structure that gives us the first output and the second output, and we see that the output is just one single value for each time. Right. So we could use that URL with the API key to authenticate from any application, be it C++, Ruby, whatever. And with that, I'm going to. You might want to also use that bit of code to print those URLs to actually, put them somewhere else, outside of the Python environment, and make sure that it works outside. But yeah, there's a bunch of things to know about machine learning if you want to operationalize it. Not really related to the algorithms, but how you put that into production. And yeah, quick word about actually the reason I'm in Madrid right now. I do training courses, and one of them is actually, the title is pretty similar to, why is it not going forward? It's pretty similar to that Meetup's title. Real word machine, no sorry, what was it? Operational machine learning with open source and cloud platforms, where we speak about all that in a little more detail. So just to give you a quick preview of what we talk about, there's some core machine learning things. Introduction, okay, model creation. I've talked about that a little bit for some of these points, but obviously more details in that workshop. And what else? And then there's some other content with advanced topics, so things like deep learning, recommender systems, and how you actually develop your own use case. So beyond the examples that you always hear about, how do you actually put that in practice? And that being said, yeah, if you want, if you're interested in that, that might be last minute because it's starting tomorrow. But we'll do that again in Madrid later this year. So do come and talk to me if you're interested in that. And with that, I'm going to thank you for your attention. Do we have time for questions?
Yes, I think we do. Any questions?
Yeah.
Yeah. So we now record voice.
Hi. Well, thanks for the presentation. Briefly, you have mentioned a flow where you describe the processing of training the model, and then you put that in production, and we recollect more information, and again that information is used to train again. The old data that you have collected should be discarded, or it should be included?
Right. So that's the workflow you were speaking about, yeah, right. So actually here it's not really that you would change the data, replace it, and so on. Here what this workflow shows, I think it's a workflow for designing a prototype where you would first want to decide, what are you trying to do for the domain of application? What's the objective in your domain of application? Then you would collect the data, so the inputs and outputs, preparing it in the right way, in the right format, develop the model. So most of the time you reuse an existing algorithm, but you could use a custom algorithm that involves more work. You would run that algorithm on your data. So that's the train model. You would evaluate it, see the performance, publish it. That's the bit that we saw with demo. Monitor what it does. So you might want to do a pilot where you use that in real life and see if it works well or not in real conditions. And then based on whether it works or doesn't work, well, if it doesn't work, then you would want to define another objective. And then for that objective, you would collect data and so on. That's what this workflow shows. And it doesn't really show the sort of the life of something that's being made, that's been turned from a prototype to to a program that's being used widely at scale in production. When you are using things when you are using models that work, and you use them for a long time, at some point you have maybe sometimes, even after just a few days, you start thinking about, do I not need to consider fresher data? Because, maybe things have changed, conditions have changed, and And in that case, it very much depends on the domain of application. There are domains where you consider fresher data like every minute, for instance, real-time bidding. So very often, other domains, things don't change so much. So you just, for instance, for churn prediction, you would use new data every month, maybe, and then the old data, where it also depends on the domain of application. If you think that, imagine that your company doesn't change so much, so the products don't change, maybe the way customers behave changes a little bit, then you might want to keep data that goes back in the past. But imagine that you change your products, or you change your target, your customer target. Maybe that would suggest to just discard the old data and start from scratch. It very much depends on the domain of application, on the use case.
Hi, thank you for the presentation. You have been mentioning your experience briefly around Azure ML. Do you have any other personal experience with other cloud platforms? Can you give us some insights or comparison?
Actually, that's one of the things that I mentioned in the workshop. So I've got a bigger slide deck dedicated to that, but the short version is that you could also replicate what Azure does with open source software, but it's rather experimental at this stage. I mean, what I've heard of is either things that are completely private, not open source, or things that are truly open source but still quite recent, so it's not really sure if anyone is using them in production. But competitors of Azure, you've got other smaller companies. There's one that's quite interesting, which is called YHAT, so YHAT. It's kind of the same idea of turning your models into APIs, and more of these cloud machine learning platforms and cloud data processing platforms, they integrate they have a feature to transform your models into APIs. I think of, for instance, Dataiku. It's a company based in New York and Paris. So they're smaller than Microsoft. But you also have Domino. I think there's another one, Domino Data Lab. There's another one which is Sense.io that was acquired by Cloudera. So it shows you that the bigger companies are really interested in that as well. And then you've got the. So what's interesting with Azure and the similar services is that you can use open source and create your own models. With your own code, maybe do it on your laptop, and then you can productionalize it, operationalize it. There are other services that make the whole process even easier. So machine learning as a service products, for instance, Amazon Machine Learning. There's a Spanish company also called BigML. They're based in the US and in Spain. And the idea is that you just provide your data, they build the model, and they sort of abstract away part of the complexity of creating models. It's simpler and quicker to experiment with these platforms than with something like scikit-learn or with R. So yeah, I think that for experimenting and for learning, they're probably a good thing to try. If you want to use a custom library, you wouldn't be able to do that with Amazon, for instance.
Okay, I think awesome. Thank you very much, Luis.
I can take more questions.
Yes,
afterwards.
we do have pizzas and beer, so please take your questions directly to Luis. We have to interrupt. Sorry about that. So thank you very much.
Staying for